Hi, I'm Fred. And I've been working on Watchman radar since World War II.
Hi, I'm Wilma. Can you explain about the switching between aux and main beam?
Ah yes. High beam, then low beam. Let's look at the horn assembly itself. Well, the upper part is the main beam horn. That forms a beam pattern closer to the ground than the aux beam. This is due to the slight downwards angle compared to the aux beam. The transmitted pulses pass through the main beam horn. The aux horn is angled a little more upwards, so it forms a pattern which is angled higher in the sky.
So, why do we need another horn? One should be enough surely.
Okay, let's look at the shape of the beam patterns. The main beam pattern looks like this. The problem is that ground returns will be received and flood the receiver at close range. That would mask targets in the affected areas. Now if we look at the aux beam pattern, the higher beam will miss much of the close-in ground clutter, avoiding the first problem. However, at long range, we could miss low-level aircraft returns, the curvature of the Earth adding to the elevation of the beam.
So, we need to use both beams to produce a compromise.
That's right, the combination looks like this. We use aux beam first, followed by main beam.
Okay, I see why we switch beams. Can we look at the practical aspects of how it's done?
Of course, here's the radar head diagram. Initially the transmitter produces the two bursts of radio energy. They get directed by the circulator towards the main beam horn as shown. Let's look now at the echoes, or returns received at the aux beam horn. These returns are amplified by the aux beam amplifier, mounted on the back of the scanner. The signal passes to the beam switch. Meanwhile, returns are also received at the main beam horn. These are directed by the circulator towards the main beam amplifier, located in the radar cabin. The returns pass to the other input of the beam switch. The main beam amp receives its power from the beam switch supply itself. That supply also provides for the beam switch receiver interface. This receiver interface accepts the beam switch waveform and drives the position of the beam switch itself.
That must be a pretty fast operating switch then.
The beam switch is an electronic device. There's no lag between one position and the other. The switch starts in the aux position and switches to main beam at about 70 nautical miles. The result passes to the receiver to be processed.
That all seems straightforward, but what happens if the power fails to the receiver interface?
Well, that power supply also serves the main beam amplifier, so if we remove the fuse, FS1, then the route for main beam would be broken. The design has allowed for this, such that, if the power supply fails, the beam switch stays in the aux position.
And what happens if the beam switch waveform is lost?
Well, of course, if the connector for the beam switch waveform is disconnected, the waveform will float high and the main beam feed would be permanently selected by the switch.
So, the returns received at the horn assembly are for 0 to 60 miles and beyond. It's the beam switch that decides whether the aux or main beam feed is selected to pass to the receiver.
Yes, that's correct. Generally 17 miles is about the range where we expect ground clutter to have dropped away. Occasionally, however, when the radar is commissioned, it may be found that ground clutter is better or worse than expected. So the switching point may vary from station to station.
Well, thanks for all that info, Fred. Bye for now.
Bye now.